Hello and welcome back to Calculus 2, section 6.5 on length of curves. So, what is the length of this chord? You would say, oh, we just make it straight, put it next to the straight edge, measure it, you're done. And I would say, great. That's exactly what you should do. If you have a rope, string, a yarn, whatever it is, straighten it up, put it next to the straight edge, and measure it, you're good to go. And now I'm going to ask you, what's the length of that road over there? All of a sudden you can't straighten it up, right? So this is a very interesting method to find the length of curves where you draw a function, x squared, square root of x, e to the x. You draw some kind of curve that has a function to it, and then you apply this integral formula that you will learn to calculate the length between, let's say, x is 1 and x is 6 or whatever. So how does this work? So we have some kind of a curve, f of x, and we would like to know the distance between the 2 points. Now, what I can do is I can draw this triangle. Now, this is not a triangle because the top is the curve, but I can approximate that curve with a straight line. Yes, there's going to be some error, but it's not terrible. Now, I have my delta x, which is the length, and I have my delta y, which is the drop in height. And I can use Pythagorean identity to come up with this red length L, right? Pythagorean formula to come up with this length L. So from this picture, L is equal to the square root of delta x squared plus delta y squared. Because, oh, by the way, if you don't know this, I'll just write on the side. Delta x is x2 minus x1 is just the distance between the two. And delta y is y2 minus y1 as a distance between the y's. So now if the distance one way is 3 and the distance the other way is 1, let's say, then you get 3 squared plus 1 square root of 10. Great. So I have my L, which is this approximated distance. That's not exactly what I'm looking for, but it's good enough. Now, what I'm going to do is I'm going to factor out this delta x. When I factor delta x, I get delta x 1 plus delta y squared over delta x squared in parentheses like that. And I factored out delta x squared. So I factored out delta x squared, and I'm left with 1 plus delta y squared over delta x squared. And now this delta x squared can jump out. So I have length is equal to delta x. Now the square and square root, they cancel. And I just have square root of 1 plus delta y squared over delta x. You know what I'm going to do? I'm just going to do this and put the square using algebra formula. Put the square on the entire fraction. So this little calculation gives us exactly what we need. We have this little L to be square root of 1 plus delta y over delta x. Isn't that the derivative? Yeah, right? So just call it f prime squared of x. And then you have this delta x on the outside. So for our formula, when you do infinitely many delta L's that are very small, you use the limit and the Riemann sum and all of that stuff. This works out to be integral a to b of square root of 1 plus f prime squared of x dx, which is that delta x from before. It's a really cool calculation. It's just that Pythagorean formula. And you have your length of curves.
So this is just an infinite amount of triangles adjacent to the curve?
Yes. So there will be another one over here and another one over here, but they are supposed to be infinitely small.
Okay.
And when you add infinitely many of them, they cover each point of the curve, and they curve together with the curve. There is no error because they're infinitely thin. They fit within each point, and there is, right? So there will be no error if you use this one. There is also the equivalent one for the y direction. So L is equal to c to d, integral c to d, square root of 1 plus f prime squared of y dy. So now you have your curves that are given as f of x, and other curves are given as f of y. You have them all. And believe it or not, lecture is over. We can do one example. And this is extremely short. It's only 2 pages in the book anyway. And now the tricky problems, we're going to do that next class. We're just going to do a vanilla example now, just to illustrate the problem. There are some very interesting examples you can do with this. Let's do something nice. It's very important, guys, to read the directions for your homework examples to stay out of the trouble. If you look, well, I don't know if you can see, I can't make this bigger because if I do Control plus, it only gives me the border larger. This stays the same inside. Good programming. Please fix it. Problems 3 to 6. Setting up arc length integrals. That already should tell you where is this going. Write and simplify, but do not evaluate. You don't have tools to solve many of these integrals, unfortunately. The whole order is backwards and then bad. We are supposed to learn chapter 7 first and then 6, because you learn methods of integration, then you go and you can do more integrals. So for the rest of the chapter 6, pay attention to the directions of the problem, and if they're saying do not solve, you don't have the means of solving that yet. So right here, but do not evaluate. So you are supposed to set up the problems with these and just walk away. That's all you are supposed to do. Now, the ones that you can do would be 9 through, and then you have the rest of the homework. So just be careful what you pick. Now, I'm going to end the class on time. I'm going to just work through number 9. By the way, the section is working through 5 exercises or so. You can read that, right? You know all the numbers and letters to read. So just look at that. Number 9 wants us to calculate the length of y equals negative 8x minus 3 on negative 2 to 6. And they say use calculus. Why would they say use calculus? Well, yeah, that too, but can you do this without calculus? Of course you can, right? This thing is a line between 2 and 6. It creates a triangle, and you can use Pythagoras to figure things out. All right, let's use calculus. So what do I have? I have my f of x as negative 8x minus 3. That means that my f prime of x is just negative 8, meaning that f prime squared of x is 64. So the length of curve is the integral negative 2 to 6, square root of 1 plus, and now I have to have this f prime squared, which is 64 dx. So this is the integral negative 2 to 6 square root of 65 dx, which is equal to square root of 65x computed from negative 2 to 6. Plug in 6, plug in negative 2, minus minus plus, so 8 square root of 65. Done. We'll do spicier examples next class because we ran out of time. So there will be part 2, the revenge of length of the curves.